Hi everyone, here we are going to see about the unit 2 continuation. So here is the question. So we have to find out the analog filter, that is HA of S equal to 6 divided by S plus 0.1 square plus 3. So for this we are going to substitute the formula, that is b by s plus a the whole square plus b squared. So substituting the formula, we will get e to the power of minus at sin bt z inverse divided by 1 minus 2 e to the power of minus at cos bt z inverse plus e to the power of minus 2 at z power minus 2. So assume t is equal to 1 again. We will get the final answer as 0.2528 z inverse by 1 minus 1.737 z inverse plus 0.818 z power minus 2. Next, we have to design the IAR filters using the bilinear transformation. So for this we have to use these steps. From the given specifications, find the pre-wrapping and analog frequencies using the formula as ohm is equal to 2 by t tan of omega by 2. So using the analog frequencies, find the h of s of the analog filter. Then select the sampling rate of the digital filter, call it t seconds per sample. Then substitute s is equal to 2 by t modulus of 1 minus z inverse by 1 plus z inverse into the transfer function found in step 2. Okay. So apply the bilinear transformation of h of s, that is equal to 2 by s plus 1 into s plus 2 with t is equal to once again, and find h of z. So the system function h of s is equal to 2 by s plus 1 into s plus 2. So substitute 2 by t into 1 minus z inverse divided by 1 plus z inverse into h of s and to get the h of z. So h of z is equal to h of s, that is z is equal to 2 by t 1 plus 1 minus z inverse by 1 plus z inverse. So that is 2 by substitute the values of for s equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Then we have to substitute t is equal to once again, we will get the answer as h of z is equal to 0.166 into 1 plus z inverse the whole square divided by 1 minus 0.3 z inverse. Okay. So the next question is, using the bilinear transformation, design the high pass filter monotonic in pass band with a cutoff frequency of 1000 Hz and down 10 decibel at 350 Hz. The sampling frequency is 5000 Hz. So the given solution is, there is pass band attenuation is alpha p is equal to 3 decibel, stop band attenuation alpha s is equal to 10 decibel, pass band frequency omega p is equal to 2 pi into 1000 and stop band frequency omega is equal to 2 pi into 350. So that is t is equal to 1 by f, we will get the answer. So pre-wrapping the digital frequencies, we have ohm p is equal to 2 by t tan omega pt by 2, and then omega ohm s is equal to 2 by t tan omega s by t by 2. Okay. So the order of the filter is n greater than or equal to log root of so that is n value we have to substitute and find out the value as n equal to 1. So the first order Butterworth filter for ohm c is 1 radian per second. Is h of s is equal to 1 divided by 1 divided by s plus 1. So that is the high pass filter for ohm c is equal to ohm p is equal to 7265 radian per second. That can be obtained by using the transformation s tends to ohm c by s. So that is 726 by 5s. So the transfer function of a high pass filter h of s is equal to 1 by s plus 1. That is s equal to 726 by s 5s. So that is a s by s plus 726. So using the bilinear transformation, the h of z, that is h of s is equal to 2 by t into 1 minus z inverse by 1 plus z inverse. So by substituting the values, we will get the answer as 0.579 into 1 minus z inverse by 1 minus 0.158 is z inverse. Okay. So the next question, determine the h of z that results when the bilinear transformation is applied to this equation. Likewise, we can substitute and find out the Next is additional examples, that is design the digital Butterworth filter satisfying the constraints. That is 0.707 less than or equal to ohm modulus h of e power j omega less than or equal to 1 for 0 less than or equal to omega less than or equal to pi by 2. Next is the modulus of h of e power j omega less than or equal to 0.2 for 3 pi by 4 less than or equal to omega less than or equal to pi, with t is equal to once again using the bilinear transformation. So the solution is that given data is passband attenuation alpha p is equal to 0.707, passband frequency is omega p is equal to pi by 2. Stopband attenuation alpha s is equal to 0.2 and stopband frequency is omega is equal to 3 pi by 4. So step 1 we have to specify the passband and stopband attenuation in decibel. So that is alpha p value is minus 20 log alpha ohms. So we have to substitute value and find out the answer. For stopband attenuation, alpha s is equal to minus 20 log of ohms. Okay. So step 2 we have to choose the t value and determine the analog frequencies, that is a pre-vap bandage frequency. Ohm p is equal to 2 by t tan omega pt by 2. That is omega pt we have to substitute. Next, likewise ohm s is equal to 2 by t tan of omega st by 2. So that is 4.828 radian per second. So step 3 is to find the order of the filter. N is greater than or equal to modulus of log base 10 root of 10 to the power of 0.1 a alpha s minus 1 by 10 to the power of 0.1 alpha p by n is 1 divided by log base 10 of modulus of alpha s by alpha p. So that n value will be greater than or equal to 1.8017. So rounding this value into the highest value, that is n is equal to 2. So step 4 is the normalized transfer function, that is HA of s is equal to 1 divided by s square plus root 2s plus 1. So step 5 is cutoff frequency. Ohm c is equal to ohm p by 10 the whole power 0.1 alpha p minus 1 the whole power 1 by 2. So substituting value will get the answer 2 radian per second. And the step 6 is find the transfer function h of s. So h of s is equal to ha of s. So we have to substitute the value limit up to s is tends to s by 2. So when you are substituting the limit, we will get the answer as 4 by s square plus 2.828 s plus 4. After the step 7 is applying the bilinear transformation to obtain the digital. So that is h of z is equal to h of s. Limit s tends is equal to 2 by t 1 minus z inverse by 1 plus z inverse. When you are substituting the limits, we will get the answer as 0.292 into 1 plus z inverse by 1 plus 0.1716 z inverse plus 9. Okay. The next question is design the digital Butterworth filter satisfying the constraints. So 0.707 this question will be given, and with t is equal to once again using the impulse invariant method. So first we have to write down the given data, that is passband attenuation, passband frequency, stopband attenuation and stopband frequency. Next first step we have to specify the passband and stopband attenuation in decibel. Okay. After that second step we have to determine the analog frequencies, that is the pre-vap bandage frequency. So omega p and omega s we have to find, that is for that formula omega p is equal to ohm pt and omega is equal to ohm st. Okay. Next step third is we have to find out the order of the filters, that is n is greater than or equal to modulus of log root of 10 to the power of 0.1 alpha s minus 1 by 10 to the power of 0.1 alpha s minus 1 divided by 10 log base 10 modulus of alpha s by alpha p.